And so again, thank you to all the attendees for joining today's Future Leaders in Robotics and AI Seminar Series. Again, brought to you by Maryland Robotics Center at the University of Maryland. Our next speaker for today is Thomas Tian. And so Ran Tian is a final year PhD student at the UC Berkeley. His research lies at the intersection of robotics and AI, with a focus on enabling robotics foundation models to serve humans at scale and in real-world environments. Throughout his PhD, he has developed new algorithms and practical solutions for addressing safety and alignment challenges that arise throughout the entire life cycle of robotics foundation models, from pre-training to post-training alignment to deployment. He also spent 2 years at Waymo working on the foundation models for autonomous driving while pursuing his PhD. His work has been recognized with several prestigious awards, including the 2024 World AI Conference Rising Star, Qualcomm Innovation Fellowship, Baidu AI Fellowship, ICRA Best Paper Award, and Robotics Science and Systems Pioneer. And so with that, I am going to stop my sharing and then allow Thomas to share his screen.
Share my screen. Okay. Share it. Awesome. Thank you for the nice introduction. So my name is Thomas. I'm very happy here to be here today to talk about my research about safety and alignment. So I think everyone will agree that the past 1 or 2 years are super amazing. So fully autonomous driving vehicles are starting ride-hailing services, and robots are entering our homes. So for the first time, it really feels like these robots will be part of our daily lives. But as we bring these robots into the real world, people are having increased concerns about safety and alignment. So to me, safety and alignment are about whether we can trust robots to act reliably in the open world, and whether robots can do what human wants. The way we traditionally handle safety and alignment is through human design. So we have a human designer sit there and figure out how to abstract the environment from sensor data into a few interpretable state variables, like X, Y, Z, and this is what we call state space representation. For example, in driving, we abstract the environment into bounding boxes of traffic agents and road graphs. And in addition to this state space representation, we also need a human designer to come up with a reward function that describes what the robot should optimize for. For example, following the navigation signal and don't collide with people. And with both the state representation and reward function defined, we fit this information into a planning optimization, like NPC, which simulates the future induced by actions and tries to find a policy that maximizes the future return defined by the human user. So we call this a model-based autonomy pipeline because it relies on explicit models of the environment and task to solve the planning problem. So this pipeline is nice because we can control how we define the environment. And we explicitly define what the robot should optimize for. And we simulate the future consequences induced by the robot's actions. So that means we can make strong statements about safety and alignment. However, as robots start to operate in increasingly complex environments, we start to realize that it's very difficult for human designers to design the structure of the problem. So I spent a long time doing research at self-driving car companies, and we need to deal with this issue a lot. So suppose I have defined the representation and reward function for my self-driving car's behavior and motion planning. And now an incident is reported back and my car is crashing into wet concrete. And I need to modify my state and reward function, which is fine, I can fix that. But the problem is that this does not stop, and more cases pop up. And eventually, human designer just wants to give up. And similarly, in manipulation, this problem is even more severe. Like if I want my robot to fold the clothes, I don't even know how to start this process. Like how do I define the state, dynamics, and reward function? And because of these scaling problems, like we start to explore directly training generative models or so-called vision language action models to generate robot actions directly from sensor data and language. And by training these models on internet scale data, we hope robotics foundation models can mitigate the scaling problems we had before. And it turns out that these models are quite powerful. not just in terms of the empirical performance, but also in their ability to generalize across different environments. However, at the same time, it is precisely this integration of these robotics foundation models raises new concerns about safety and alignment. So this is an example from Google's robotics foundation model released about 2 weeks ago. So in this video, we see the human user wants the robot to upright the plant. And it's very interesting that without any hesitation, the robot goes for the plant itself instead of holding the box. So this is actually very dangerous in real life because I don't want my robot to break my plant. And this is another interesting example. So here, the robot is using an LM to plan actions. And if we look at the action outputs from the LM, one of the most likely task plan is to put a metal ball in the microwave, which is very unsafe and should not be generated or assigned with high likelihood. So from my own personal experience in both academia and industry, I have seen the values in robotics foundation models. These models can be trained with large-scale data and learn to compress high-dimensional sensor data into meaningful representations and pick up generalizable action priors. But because these models are trained end-to-end on large-scale data with limited supervision, they are not explicitly instructed to optimize for human values, and often lack understanding of the consequences induced by their actions, and they often struggle to recognize their own limitations. And interestingly, like all these limitations seem to be the advantages of the traditional model-based approach. So throughout my study, I have been thinking about this question: how can we generalize model-based principles and make them compatible with general AI so that frontier robotics models can become safe and controllable and ultimately towards safe and aligned embodied AI? And I have been working toward this goal across the entire life cycle of robotics foundation models, from pre-training to post-training and to onboard development. So for today's talk, I want to share a little bit about how we can use generalized model-based principles to make robotics foundation models behave according to human values. So a fundamental technique that this robotics foundation model relies on is behavior cloning, which is about learning a policy directly from human actual demonstrations dataset. So each training sample in the dataset consists of 3 elements: the context of the task, like description, and the observation of the environment, like images, LiDAR, and the human expert actions. So the goal is very straightforward. Like, we want to train a policy model that maximizes the likelihood of human actions, conditioned on the context and the observation. And here is a problem. So this objective is just a proxy for what we actually care about. What we truly want is to optimize for the reward function, the underlying principle that incentivizes human behaviors in the first place. So despite powerful models and larger data, we always use the misaligned objective to train the robot's policy. As a result, by optimizing an incomplete objective, these models lead to undesirable behavior at best and safety violations at worst. So let me give you a concrete example about this misalignment. So here we train a vision language action model to assist the user using behavior cloning and open source dataset. I want the robot to help me grab a bag of chips. And here's what the robot did. So it looks like the model has learned the task successfully, right? It picks up the bag. But instead of grasping it carefully, it squeezes the middle of the bag by completely crushing all the chips inside. And clearly, I don't want this. So how do we solve this misalignment problem where these imitation-based robotics models are not optimized using human preferences? So a very nice approach to tackle this misalignment problem is reinforced learning from human feedback, or RHF. And RHF works in 5 key steps. So first, we train a generative model using behavior cloning objective on human demonstrations, just like before. And this gives us a pre-trained imitation model that can generate decent outputs. And next, we show the pre-trained model's outputs to a human expert and collect their preference rankings. And from this preference ranking data, we train a reward model, and that evaluates like how good a generation is. And finally, we fine-tune the model to optimize the reward function by encouraging it to generate outputs with high reward. So this approach is exciting because it brings together the best of two worlds. On one hand, we are leveraging the success of and the scalability of powerful generative models. And on the other hand, we are bringing back a key model-based principle, which is explicit optimization for what humans truly want. So instead of just trying to memorize the training data, the model now is being actively shaped by human preference, which makes it much more aligned with our goal. And recently, RHF has demonstrated great potentials in improving performance of non-embodied generative models, like LMs, text-to-image generations, and video generations. But despite its success in these non-embodied applications, preference alignment has not yet demonstrated the same impact when it comes to aligning robotics foundation models in real world. And why is that? It might seem straightforward to apply a similar pipeline. We show user model generations and ask them to rank the model outputs and use these rankings to train a reward function and finally fine-tune the model to optimize the reward. But the critical difference is that unlike text or images, robotics foundation models involve an actual robot in the learning loop. And here, even though the outputs from the model are actions, what the user observes are deployment videos of robot behaviors. And the reward function is a visual reward function that maps the high-dimensional observations to reward values. And this distinction makes collecting human preference feedback significantly more expensive because the end user has to wait there, watch the robot doing its stuff, and provide preference rankings. So we did an estimation on the human effort. We need to run alignment on some of the common manipulation tasks. And for each task, it would take 3 weeks to collect enough data to do effective post-training preference alignment. And therefore, if we hope to align generalist embodied agents effectively, we must find ways to minimize the reliance on human feedback while still learning a high-quality visual reward. Okay, so how do we do visual reward learning? And specifically, given a deployment video, how should we assign its reward value? Intuitively, this reward is generated by comparing it with ideal behavior in the human's mind, like the scale of the similarity determined by the human. And mathematically, this process can be modeled by first using human's visual encoder by age to encode this robot deployment video and the ideal behavior video into feature distributions. And then the reward signal is generated by matching these 2 feature distributions. Intuitively, if the robot's deployment video's feature distribution is really far away from the desired feature distribution, then that means the behavior is probably bad and should have low reward. And over the years, researchers have explored different divergence metrics to perform this matching and generate rewards. However, regardless how you do this feature matching, it must happen within the end user's visual representation space, which is unknown to the robot. This implies that a critical aspect of learning human reward function is learning how human users abstract visual signals into important features, a challenge formerly known as representation alignment problem. So instead of trying to learn the visual reward in a single end-to-end process without considering the structure of the problem, we propose a divide and conquer approach by leveraging the structure of the problem. So the key idea is that we focus the limited human preference budget exclusively on aligning the robot's visual representations with those of the end user. And this way, the robot can better understand what truly matters to the task. And once the visual representation is aligned, the visual reward signal can be directly generated using feature distribution matching. Okay, so let's see how to solve this representation alignment step by step. So the first step is the same. We ask human to rank couplets of robot deployment videos based on their preferences. And with these preference rankings, we could implicitly learn the robot's encoder phi-r by maximizing the probability of these preference rankings. And to do this, the most preferred video is treated as an anchor, and the other 2 videos are compared to the anchor in terms of their preference similarity. We interpret the probability of a preference ranking using this Berkeley model, And essentially, this equation tells us that the probability of one behavior being preferred over another depends on their distance to the anchor. The closer a behavior is to the anchor, the higher its probability of being preferred. Conceptually, this is very similar to contrastive learning in computer vision, which tries to induce a representation that makes visually similar images closer in the latent space. And in our case, the one key difference is that the notion of similarity is driven by the end user's preferences. So if two behaviors are similarly preferred, then their features that matter to the end user should be similar in the representation space as well. And our hope is that by optimizing for a representation that enables the robot to clearly distinguish between preferred and less preferred behaviors, we hope this representation captures the informative attributes that truly matter to the end user, and ultimately resulting in a visual reward function that effectively aligns robot behaviors with end user preferences. We call our approach representation-aligned preference-based learning, which is an observation-only method that learns visual reward signals with significantly less human feedback, enabling effective preference alignment for robotics foundation models. So the key argument I'm trying to make is that allocating human budget exclusively to align visual representations can effectively reduce the reliance on human feedback during policy alignment. We first verify this in a simulation environment. So there are blocks with different shapes and color on the table, and the robot needs to push the rectangles together to the goal region. And since this is the same environment, we can write down the ground truth reward. So we use this ground truth reward to collect 150 preference rankings. And we gave this same data set to both the conventional RHF method and our approach to do preference alignment. And remember that the conventional RHF method also uses human feedback to learn visual reward, but it does not consider the structure of the problem and doing everything end to end. And this is the policy learning curve induced by different rewards. We can see that with the same amount of preference data, the conventional RHF method barely learns anything useful. In contrast, our method can learn a very good policy. It's very surprising that the conventional RHF fails to learn a useful robot policy, especially since it also uses the same amount of human feedback. This shows that focusing human preference data on aligning representations significantly reduces the need for human feedback, while still learning a high-quality visual reward for effective alignment. And we also experimented with cross-embodiment transfer. So we learned the visual reward signal using human videos, and we deploy this reward on two different robots in simulation environment, Franka robot and Kuka robot. And it's exciting to see that in addition to be sample efficient, our visual reward can be effectively generalized across different environments and different embodiments. We also tried our approach in real world to see if the benefits still hold up. So we start by training a vision language action model using behavior cloning on open source dataset. And we tested this policy in the real world tasks like picking up a bag of chips and picking up and placing a fork. And as we saw earlier, the robot swings in the middle of the bag, crushing all the chips. And in the pickup task, we can see that instead of gently placing the fork as humans would, the robot simply drops it. So I really want this robot to act in ways that I'm happy with. So we collect 20 human preference rankings to align the pre-trained VLA model. And here are the robot behaviors after the post-training alignment. And in the picking up chips task, we can see that the robot grabs the bag by the corner instead of squeezing the middle, avoiding damages to the chips inside. And in this pick and place fork task, we can see that the robot gently places the fork in the bowl instead of simply dropping it. And from our evaluation, we observed that our preference alignment approach has significantly improved the pre-trained VLA model's alignment score. And compared to the conventional RHF, our preference alignment approach can triple the alignment score using the same amount of human budget. And in the robotics manipulation setting, we consider the preference alignment of a single agent. But the same idea also applies to a much larger scale setting with multiple agents acting in the environment, such as traffic simulation. So we first train our 1 million parameter traffic simulation model using this behavior cloning objective. And to evaluate this model, we use a metric called model realism, which measures the model's ability to generate human-like traffic simulations. And here we compare the realism score of our pre-trained 1 million model with current SOTA models. As we can see, our model's performance is quite poor. This isn't surprising given that our model's capacity is only like a fraction of these SOTA models. So we want to apply our preference alignment approach here as well to distill human driving preferences into this traffic generation model. So we start by collecting a small amount of preference feedback on traffic simulations generated by the pre-trained model, and this feedback can help us learn the informative attributes that explain why a human expert might prefer this simulation over another simulation. And using these aligned representations, we build a reward function for evaluating the quality of a generation. And finally, we use this reward function to fine-tune the traffic simulation model. And here is the model performance after applying the preference alignment. And remarkably, our post-training alignment approach uses just 5,000 preference rankings to bring a 1 million model's performance to a level comparable to a 100 times larger SOTA model. And here are some examples of traffic simulations produced by the model. And on the right side, on the left side, you can see the performance of the pre-trained model. We can see that the vehicle is too close to the pedestrian. And in the bottom case, we can see that the vehicle is nearly crashing into the front vehicle. And after the alignment, we can see that the vehicle learns to yield to the pedestrian and also behave and also show a human-like stopping behavior without crashing into the lead vehicle. Okay, so just to summarize, we talk about using generalized model-based principles to make robotics foundation models behave according to human values. And we do this by generalizing state-space representation and reward functions into visual latent space by representation alignment. So we can effectively distill hard to specify human preferences into these robotics foundation models. And the key message I want to send today is that data scaling is not enough to ensure safety and alignment of robotics models. And one potential solution is to generalize model-based principles and make them compatible with generative AI so that frontier robotics models can become safe and controllable and ultimately towards safe and aligned embodied AI. And this is the end of my presentation. And thank you so much for listening. And I'm happy to answer any questions.
Thank you, Thomas. That too was a great presentation. Do we have any questions from the audience? So while we wait, I do have a couple of questions myself. So around slide 26 is when you started introducing this idea of preference ranking. I'm curious about how you handle different people preferences, right, in the ranking process. Is this trained by one subject and that's the preference of one subject?
I mean, 26. 26.
Yeah, I mean, any of these will do. Yeah.
Okay. So that's a very good question. So for some tasks, right now, we don't consider multimodal preferences. We only consider there's like one preference exists in the data set. And this assumption works in some settings, for example, traffic simulation, because like all the drivers share a set of common rules. For example, don't crash into other people, and don't violate traffic rules, and don't cross solid lines. So for this type of settings, it works well. And in personalized alignment setting, it also works well. But a great challenge is like when you collect this preference data from like a multi-source of like multiple people on the internet. Like how do you learn these multiple preferences and select the one that is most suitable for you? And actually, this is actually a future work for our study, like how to extract this multi-preference from the noisy data set. But for the works you saw today, we only assume there is only one preferences existing in the preference rankings.
Excellent. Yeah, no, and you kind of touched on what would have been my second question, and I thought about it in like slide 6 to 7 or so. Is that if you are given references for other rankings, right? People have already kind of ranked their preferences. Can you not learn, right? How people might rank their preferences just on a couple samples, given that you've already seen, kind of these patterns, and I can envision
Yeah, exactly.
different
Yeah.
photos, right?
Yeah, like for example, my preference may be suppressing your preference. And because it's suppressing effect, like we might not learn anything useful from the noise data set. So it's extremely important to learn how to identify multi-source preferences in the data set and how to select the one you need and suppress one you don't need.
Absolutely. Yeah, and I can also see how somebody might be observing different things, right? So even the feature that you're learning, right, can play a big role in that.
Yeah.
Thank you. Do we have any questions from the audience? We have time for a couple questions. So I'll take the opportunity to thank our speakers today. We have one more seminar coming up in a couple of weeks on May 9th. That will be the last seminar for the future leaders in robotics and AI for the semester. Please do join us then. And reminder that if you want to see the recordings from prior presentations, you can visit our website, robotics.emd.edu/future leaders. And see the recordings for previous semesters, and then later in the semester, we're going to be uploading the presentations from this semester as well. Thank you all for attending, and see you in the next one.